Hello everyone, I'm sure you're doing awesome. So this is an entirely new series and this is going to be a very descriptive and very hands-on oriented series for the app generative AI and especially for the application developers. So let's start with the utmost clarity, like for whom exactly this lecture series is so that you don't really waste your time. In case you are a machine learning engineer, uh, in case you are working on a completely research layer, then probably this video series might not be for you. And in case you are an application layer developer, this is the perfect video series that you might be looking at. So let's start about the detailing of these two engineering discipline that has emerged in the last only a couple of years in the market once the AI frenzy come or that AI bombardment come into the industry. So when we are talking about the research layer basically are the PhDs, the mathematicians, the deep learning researchers, the specialists in calculus, the people who are doing linear algebra, doing back propagation, and what exactly they build at the end of the day. In the OpenAI or in the Google DeepMind, in Anthropic, they basically build the model artifacts. So when we see the actual model, like ChatGPT is end of the day a product, right? Behind the scene it uses GPT 3.5 or GPT 4, or the till the day it is recording it is GPT 5.2. So they are developing those application which are behind the ChatGPT. But when we are talking about the ChatGPT or any other agentic application, those things are developed by either backend engineer or the cloud engineers, the DevOps, SRE, platform engineering, many other disciplines are associated with that. So that is basically the application layer. So I just want you to understand this that difference of ChatGPT and GPT 5.2. So GPT 5.2 is the model. Okay. So this thing is the model, and ChatGPT is nothing but an application that is built on top of the model. Okay, on top of the model. So our concentration is particularly on this part where you will be using the model. You will be developing multiple applications. For example, those frozen model artifacts. So when I use this language, the frozen model artifact, just take cloth sonnet 4.5 or GPT 5.2 or the DeepSeek 3.1. These are the frozen model artifact. And how exactly you are going to pass that your application data to those frozen model, that is the responsibility of the application engineer. The ML engineers or those research people are not bothered about this part. Their only concern is how well this this particular model behaves, and in many specialized use cases. But the development of those use cases, and the chat interfaces, the RAG pipelines, like the coding assistants, for example, the cloth code or the GitHub Copilot, those are the things that are being developed by the application layer or the application engineers. So in case you want to come into this area where you want to do the application development using those hard frozen models, then this particular video series is for you. But again, I'm repeating, it is not for the machine learning engineers, it is for the application engineer who, by using this artifacts or the models, are going to create various application on the generative AI. And not only gen AI, there are some other aspects of it as well, for example the imageries and other things which we will come gradually over the time. So now that you got the idea that whether if this course is for you as an application engineer, so let's take a little bit of deep dive into it. There is this research layer, right? So what does this research layer do? The input that you are giving, all the raw text data sets, it keep on crawling them. Okay, this is basically the input of it, and based on those input, what it does is it trains that particular model, and there are many nuances are there, like forward and backward pass. There are the weight updates, and the update is a model weights file where you create the actual model. And uh, whereas if I just compare it side by side with the application layer, the input over here is simply the user queries. End of the day, user queries or the business logics, those things are the input, and you are not going to train anything using this application layer data. Okay, so research people only train the complete model and create it. And this part, I also want you to understand the CapEx and the OpEx. So CapEx means there are some capital expenditures, right? So because you will be running this huge training process, there is a huge infrastructure needed and a lot of costs, and the iteration is generally goes for the months and sometimes like half of the years. But whereas here it is OpEx model. OpEx is like the operational expenditure. So when we say operational expenditure, that means mostly around your basic operations of API hit or the basic scale up, scale down, that is that you want to do. So here the API endpoints, like in case you are doing RAG pipelines, then there is a certain extension of PostgreSQL that we will come in some time. All these things we are going to cover. But the point is, like here, we in the application layer, the scale of operations are really limited. Whereas here it is like full of iteration, full of cost, full of huge infrastructure. So like in case you have understood this, let's take this scenario. Okay, so this is just a scenario that I prepared for you, and if you can understand the scenario over here, probably you understood the basic differences that we were talking about, the application layer and the research layer. And trust me, in many organizations, when I consulted with them, I found out that even at the leadership level, this kind of vagueness is there, where they don't really understand where does a capability of the research stop and where does the capability of the application engineering start. That is because definitely AI engineering is a very fresh domain to get started with. So let's take this scenario. So suppose you are being a principal engineer at Uber. Your data science team proposes to training a custom LLM from scratch, okay, to handle the customer support tickets. So for example, the flow generally happens with this cases is like the moment the customer asks something, it will generally go into that direction, that whether the customer wants a refund or customer is looking for a specific resolution or some sort of a theft or some sort of like the ride is not coming on time. Those sort of problems, this bot or this custom LLM that they are trying to develop will be able to understand. And the argument that this data science team is giving is like our support conversations are definitely unique, because it's a completely private data. So ChatGPT, sorry, the GPT 5.2 or Claude or any other frontier model like Gemini, they might not be, not only might not be, they will not be aware of the conversations that we are taking. Okay, so we have almost 10 years of ticketing history, like 100 million tickets are there, and we will we will be able to constantly fine tune the model to understand what exactly the sentiment of the customer. So the data science team is very much pushing towards this direction, that they want to take a completely new research layer. They want to develop like the research layer that we were talking about. And you as a principal engineer have to gauge that whether this is a sound argument or not. So you have to make a recommendation, and should your Uber engineering team train a model from scratch, or whether they should use an existing foundation or the frontier models via API, or there are options like self-hosting also. We will gradually come into those things, like what is the difference between self-hosting a model and accessing it via API, or any of the cloud hosting like Amazon Bedrock or Azure AI Foundry, and what are the Three primary engineering constraint you would use to argue against this training, to this whole process. So I'd just give you like some time to think about it. You pause the video and then come back. We will discuss it in detail. So, as a principal engineer, your argument would be probably on this five pillars. So, the first is the compute. What exactly is the compute requirement? So, if you see, like a normal GPT-3 scale model, like according to the OpenAI's GPT-3 paper, if I just think GPT-3 is a little older one, right? Still, it's a 175 billion parameters it have, and the moment we are talking about this many number of parameters, there is a huge amount of compute is needed around that. And again, I'm not trying to quantify it right now, but that compute is a lot in terms of when we are starting a project from scratch. And the hardware is another problem. So the hardware we are going to need over here is almost like 80 GB VRAM each. There are 1000 plus GPUs at least we are going to need, and with 80 GB RAM each, VRAM each, we are going to need it. The duration will be close to 6 months just to train the data, and then there might be some further iterations might be needed. So keeping it on a higher side of numbers, that comes into uh, 6 months. And what is the cost? So cost, again, like if we just do a very like a high level cost, like if I go by the paper of the OpenAI GPT-3, so the cost would come somewhere around like 10 to 50 million. Okay, 10 to 50 million dollar, right? So here you can see that like the amount of compute, the amount of hardware, the kind of duration and the cost, it is already very high, and the team also have to be very skilled. They are generally like high skilled ML researchers has to be there, because this is a very niche field where we have to get the best in the market to understand around these things. So hiring this team and then training this data and further scaling up this infrastructure, taking 6 months just for running it, probably like we are looking for a 1 year minimal runway with a huge cost. But if you are using open AI's API, or like any other API, for example, the Gemini or like Anthropic, then you basically pay per token. Okay, so for OpenAI or Gemini, if we are using this, then we are going to use in a pay per token model. Okay, it is simply a pay as you go model, and API will handle their own scaling. The integration with there is something called retrieval augmentation on generation. So in the RAG, it will probably take like complete integration of 4 weeks. That means a month, and the cost will be, you can see, like because it is a paper token, so generally it is very less, like 0.002 per dollar per to 1K token, I think. Yeah, so $2 per 1K token. So if you process like even 10 million tickets per month, that is like coming around 20K per month and 240K per year. So, and a team of simple like two mid-level engineers will be able to do it. So our argument will be on this is training from scratch is a pure capex. Okay, it is a capital expenditure that we have to do, millions upfront. And here, whether we are using the APIs, it's a operational cost, which is a OpEx model. Even if API cost reach like 1 million per year, it is still cheaper than even the initial investment that we had. And I'm not going into the like detailed cost envelope, but if you just read the OpenAI, the three paper, the GPT-3 paper of the OpenAI, you will find this. So plus all the time to market and the other, like for example, here not only this, we can even fine tune the model. Okay, we instead of a completely scratch model, other than RAG, if we do fine tuning, probably it will take a little bit more time. I take it as a 6 weeks. So still in every aspect, the moment we are going into this model of using the existing um, uh, existing popular foundation or the frontier models, it is becoming a very easy easy game to play. And also there is another important part is the data scarcity and the generalization. So although intuitively the team might say that our tickets are completely unique, but LLMs, when we are talking about LLMs like GPT 5.2, they are trained on trillions of tokens. Okay, so when these things are trillions of tokens from the internet, and like the books, Wikipedia, Reddit, and whatnot. So this gives them a very unique thing, that is the language understanding, the grammar and the syntax, and the world knowledge. And another one important thing is the domain transfer. Okay, even if they haven't seen the tickets, they might have seen like thousands of conversations. Okay, so this is going as per the OpEx model that we are talking about. So for the operational expenditures, these things we are already getting without spending anything. So for 100 million Uber tickets, or even maybe a billion Uber tickets, are a tiny fraction to what even the GPT, forget about GPT 5.2, even the GPT 4 has seen. So the better approach will always be like, we have to start with RAG or fine tune, and then we can always come to a particular conclusion that whether we are going to do RAG, retrieval augmentation and generation, or the fine tuning. So this definitely will will explore a lot of details, what exactly the RAG is and what exactly are fine tuning details in following videos. But this is for just for your understanding, like where exactly the application developer comes, and how even in engineering frontier this argument is always winning. Like multiple times in the like I do consultancy with some of the organizations. Multiple times I have seen they were going into this direction. So when I asked them these questions, and we just ran a very small POC, like how good the RAG or the fine-tuned pipeline is, everybody, like from the leadership to the engineers who were even pushing it for the CapEx model, that they want to do their self LLM, they all agreed that using this application layer would be a um, way more better approach over here. But of course, like the other things are also being taken care, right? Like the data security, everything which our organization cares. But right now we are just sticking over here onto this basic arguments. So let's talk about how LLM work and why it is important. So why it is important to you as a application engineer, like you might argue that right now we were talking about that those internals are completely hidden from me because that has been taken care by the research layer or the machine learning engineers who are the PhDs, the mathematician. Then why do I at all care about what is the core primitive of the LLM's inner working? And the reason we as an application developer have to have some idea is basically, unless we understand this, we might get into the debug hallucinations. For examples, like we can run into very high token probability, like we do not even understand how internally it is working. So if we go into that and we keep on debugging, and we will just think that using high token will give us a higher probability um, of getting a better response, but that doesn't happen. And of course, the architect the conversation system, for example, how the stateless APIs can interact with each other when you are using an agent, how it does the tool calling, understanding like tool calling and architecture of stateless agents. That is also very much important. Unless we understand the inner workings, we will not be able to do that. And then like optimizing cost, designing the prompts, because the in over here, although prompt engineering we will not be discussing a lot, but still prompt is one of the key part. How good or bad our prompt is sometimes totally direct how good or bad our system is. So often this wrapper sort of a system, what happens is they just change their internal prompt or the internal master prompt a little, and sometimes their model completely starts behaving in a different way. So let's talk about what is the core primitive in further details. So let's take a like a very high level around 10,000 feet walk through what exactly happened when we are having a conversation with ChatGPT. The first and foremost thing that I want you to understand is LLM are stateless. Though we are seeing the chat history in ChatGPT and we can do a follow up sort of a thing, but LLM as a unit is always stateless. And this particular sequence diagram, if we understand correctly, then probably we are uh, clear on our path of understanding what exactly LLMs are doing internally. Then we will be able to go further towards the mathematical intuition. So what exactly happens is, like, initially user suppose give a message that I want to plan a trip to Paris. So your application server or state manager, whatever you tell it, gets this message, and there is always an intermediary layer which generally tells you whether there is any recent conversation history or are present or not. So that is where this conversation history comes in. So the data on your ChatGPT left hand side panel that you see, where you see all the chat history, that is basically coming from this Redis or this temporary, not exactly temporary, this key value pair database that they have, where they fetch the conversation history, and once they fetch it, what is being done is tokenization. That is one of the most important word. We will come into a lot of detail in some time, but just understand LLM cannot read this word in this way, like I want to plan a trip to Paris or something. What it does is it breaks it down, this text, to some kind of a token, and we will definitely build a tokenizer over the time to understand it more, what exactly the tokens are doing and what the LLMs are doing internally by using those tokens. So what exactly happens is, this using these tokens, then a post request, a simple service call, nothing else, a simple service call is being done to the LLM API, and there they further tokenize the input. And after tokenization, so tokenization can happen in this stage as well, like where we are trying to like tokenizer can be at this level or even within the LLM as well, that like it is completely the design of the application. Either they tokenize it first and send it across, or they send completely a raw text to LLM, and LLM has to implement it separately, this tokenizer at the LLM API. So ideally, it is better to visualize in this way, that this application server and this this three guys, they work very closely. This is a very okay thing to visualize. And then after it is getting tokenized, it is being passed on to here. So right now this part even you can ignore, but let's keep it there. So after you get that tokenized tokenized data, what happens is LLM then passed on to their model internals, and in those internals many things like embeddings, attention, logits, everything we will come gradually over the time, what exactly embeddings are, what exactly positional encodings are, what exactly attentions are, feed forward network, all these things we will come in detail. And then this LLM also like do some probability of all the responses it gets. So against this token, LLM get like multiple possibilities. okay, or multiple probabilities, I would say. So out of that, it determines that what is the closest probability it can get, and that too depends some way into the temperature. We will uh, do not get overwhelmed with it. We will come on to this. So what happened is, after this, a certain probabilistic response, it um, it totally gives back to the LLM, and then it generates the token, and further from this token to text conversation happens, and you will see that this message will go through. Now the very interesting part is when the second request comes, LLM by default, this API, when we are talking about the LLM, this API is completely stateless. Why I am saying stateless? It has no idea what has happened during this particular request one, the first message. Okay, so the request two will be a completely uh, independent message that will go through. So suppose you ask another question, what is the best time to visit, and it will now fetch the conversation, and it will find that, okay, this conversation is already there. So now there comes the one of the most problematic or one of the most challenging area for the application developers, that is the context window. So now, as a context, we have to send the entire history. Now we cannot only send this part, because LLM particularly doesn't have any memory of what has happened during the request 1 life cycle. So this request 2 is being sent with this complete conversation history, and what happens is it has to tokenize the full conversation. So now, for example, Gemini, you might be aware that 2.5 onwards Gemini used to give like 1 million token window, but that is a cause of huge cost, because now in the next message it not only has to tokenize this part, that what is the best time to visit, it has to tokenize this part as well, the whole response as well, and send this particular post request. Okay, so this is the important thing to note, like LLM has no memory of the request. LLM has no memory of the request one. It only sees what is there in the request. Okay, so now it is being passed on to again the generator, and the messages and everything again passing through the forward pass, using the softmax, the probabilities, the temperature, all the details. Uh, it is being returned that what exactly the response would be. And here also it is very interesting that after that it is being appended. It is just like a list dot append, nothing else happens after we get it, and in the conversation history the next message pops in. Now, suppose for some reason this history part is not working, like history part you are saving in some sort of a internal database, like when I was researching about few of the very popular one, like the DynamoDB, or uh, like sorry, any other popular chats, not exactly the LLMs, the chat, like the DeepSeek and stuff. So they use behind the scene for their history, for maintaining those history, databases like DynamoDB, or databases like sometimes the Redis is also fine with the complete permanent snapshot, they use it. And if we do not save it, this how much will it cost? This particular message will go just as a simple message, like nothing will happen, and the LLM will not understand any context, and they might be wondering like what exactly you are talking about, what is the cost uh, you are asking me over here. So it might have it might tell you that I do not have enough context on this. So I hope you got this part. Like in case you got this deep dive into what happened behind the scene into ChatGPT, then probably this is a very big foundational concept that you should be solidifying upon as an application developer, because your application, no matter how complex or how difficult it becomes, the basic architecture will be always this. So when you will go to your like leadership executive summaries, always this will be one of the basic architecture that you will be explaining them, that this is how I'm implementing something, and RAG fine tuning everything will come on top of this. Somewhere down the line they will be introduced here or here or here, somewhere down the line they will be introduced. Okay, so this is the very core of the message. uh, so now let's try to understand this part. Is this part LLM is really a magic? We will gradually come into the different part, like what tokenizers are, what temperatures are, forward pass and everything. So when we are talking about LLM, is it really a magic? So I'm going to make a very pinpointed statement and try to explain it to you gradually. So LLM, stripped of all the AI magic hype, it is basically a large language model. It is nothing more than a deterministic function that maps a sequence of tokens to a probability distribution. So, what kind of a function is this? Suppose I am writing something like the sky is, and I press my enter button over here. Okay, I press my enter button into my chat. So now what would happen is, it the LLM would at first tokenize it. Okay, so after tokenizing, the output will be like this. So the will become 1062, sky is 13356, and is 374. All the numbers I am just making it up. So what would happen is, there will be a very basic function will be passed on to the LLM, and you from your side will be calling this function. What is this function? We don't know what internally the function is written. This is being developed by those ML researchers that we were talking about. So this sequence will go through the embedding layer, the multiple attention, the feed forward, then the final output layers and everything. So what it would try to do is, it will try to produce a vector. Okay, so how would the vector look like? That again is a completely mathematical thing, but over the time, like when you apply when you get the output, so output will look like something like this. Okay, so again, I'm not going into the embeddings and the all the other details right now, but let's talk about the how the output is there for this particular one. So output is something like that. When you input it, so yeah, when you input the sky is, so these are the, suppose the probabilities are being returned. So sky is blue, it has a probability of 0.7, quite good probability. Sky is cloudy, it has a probability of 0.15. Sky is falling, it has a probability way lesser. And sky is banana, this is a probability of very very less. So what happened is, the system doesn't return all the probabilities, it samples one token based on the distribution. So as the LLM keep on generating it, what happens behind the scene is, it uses something like a greedy decoding sort of a thing, and out of this, like picking the highest probability, and there are lot many other probabilistic functions are there, but just for our use case, think like it picks the highest probability, and it will give you sky is blue. Okay, so the full completion becomes the sky is blue, and this is called the auto-regressive generation. So the input will be something like 1082 and all the other things that we saw, something like this it might become, and then the output becomes this, that is the 582. And then what happens is, this data is being fed onto this, and further, if the output is like dot a full stop, then the full stop will be applied, and it is being generated, like it keep on generating, keep on generating the output. And how it generate? It is in a auto regressive manner. So LLM, like let's go back to this statement again. It maps a sequence of token to a probability distribution. So once you give something, it just keep on creating a single token, and that single token goes on to the next one, and further that whole response is being generated. And of course there are stop sequences and the other things that happens internally, but the idea over here is, at a time, if I just strip off all the hype, at a time only a single output is appended on the input, and that input is gradually getting augmented, and the term that is being used over here is auto regression, or the auto regressive manner the output is being generated. So it might be quite strange at the first glance, but that's exactly how all the current mainstream LLM work. They generate text token one at a time. Text token generated one token at a time, and then gradually through auto regression it keep on building through the auto regression. So this is the very core of the LLM, and LLM is not at all a magic. It's just some token it is generating time to time. That's all. Now, so then you might be telling me, I don't trust you at all. Then how come something passing, like sometimes we see that although we are passing the same question, we get the different answer. So there the internal sampling comes in play. So using the internal sampling, what LLM does is they introduce some sort of randomness into the answers. That is why, like often in a two different questions you might see some two different answers around it, and it is completely being injected by the LLM sometimes at the runtime, or we will just in some time we will discuss about things like the greedy decoding, the temperature sampling, like the top p nucleus or the top k sampling. Those things also will come into the play. So suppose we may ask, like, tell me a fun fact about octopus. Okay, a simple question like this. Now what would happen is, at first the LLM would compute few things like the probability of octopus, fun, all these words it will find. But suppose the temperature, okay, temperature is define the randomness. Temperature defines the randomness. If it is zero point 0.8, then that means like there will be a certain randomness will be introduced. High temperature means like a further more randomness in the answer, and if the temperature is lower towards like zero, that means there are the answer will be more deterministic or in a more specific in a way. So let's talk about like uh, about this output layer, the logits, the computations, everything with another example with complete details, so you get the full idea. So this is a second example. So suppose the input sentence we give and press a enter after writing the cat sat on the. Okay. So the first thing that happens is definitely the tokenization that we were talking about the moment it is being passed on to the API. So if we use something like a tick token, okay, what it does is it can do the encoding for the model GPT-4, and it creates that. So you can just pass this thing and you will see that there are like 5 tokens will be generated. Okay, so 1 2 3 4 5 words are there and 5 tokens will be there. And then this token is just an integer index into that vocabulary. Okay, it is more like a mapping sort of a thing that is happening. So after that what happens is the model processes the sequence. So over here, what exactly happened here? Like a lot of things happen. So we will just simplify it for the time being. So there is an embedding layer. So that token ID will be converted into a n dimensional vector. So these vectors, what it will additionally would do is alongside this vector there will be positional encoding. Positional encoding means it will tell that okay, this is the zeroth one, this is the first one, this is the second one, something like that. Why it is important? Because if we do not have the positional encoding, the reverse of it might cause a problem, because it will be a same set of it will be a same set of vectors that we will have. So positional encoding, why it is important, we will explain with another example, and trust me, you will understand it by the end of this video. And then there will be attention layers. So what attention layer does is it creates a kind of a mesh where it looks at every other token to understand the context. Okay, that too we will cover in the our next section. Just understand it internally what is happening as an example. And after that, the output layer, it produces like a vector sort of a thing, a vocabulary. So the the output layer, the thing that it produces is logits. So what exactly logits are? Logits are basically like the raw scores. So whatever the raw score that we get against every single output, as we were talking about the probability of the output, so raw scores is being called as a logit. And then what happens is the model, through softmax or any other probabilistic distribution function, it tries to understand is like what are the most likelihood in terms of the probability. So after that, like softmax is a numpy function, we can just use it as it is. I will just show you how the code looks. Give me a second. Okay. Yeah. So in softmax, what will happen is in softmax, we are going to just have the probabilities defined over here. You can see the mat has the highest probability. And if you carefully see, the total generally always sums up to 1, because that is the probability. 1 means it is the total 100% of the cases it covers. And if we just keep on changing with the temperature over here, so temperature 0, okay, temperature 0 gives you a greedy decoding. That means the most highest, probability it will be get selected with temperature 0. And temperature 1, it will go through sampling like many other data it will go through. And temperature 0.5 is also a little bit more deterministic, of course more deterministic than 1. So temperature 1, when we are marking it as 1, it will introduce extreme level of randomness, okay, or extreme level of diverse sample. So again, so this is the process. The whole sentence will be being generated through a auto-regressive loop, because there is always something called a stop sequence. Suppose there is a sequence limit or something that is being defined. Before that, LLM tries to adjust to stop the complete response that it is generating. In case you have understood it, let's dive into this checkpoint question. This will give you a utmost clarity what exactly happening behind the scene if you are able to solve this. So suppose you are designing the backend for the WhatsApp AI assistant. Like WhatsApp suddenly comes to your organizations and tells ki, um, look guys, we want some sort of a complete AI assistant. And what this AI assistant will be able to do is, like, suppose I have talked to someone, I have talked about flight to Paris in some other conversation. I want you to remember every single thing. Okay, so this will be a bot. Also, it will generally go to the different conversation and fetch few things. So how would you architect the whole backend on this? So this is completely like the real world problem as a backend application engineer what you will face. So the backend, for example, all these details, like architecting the backend, the latency, the cost, and what is the breaking point, like the context window. These are the very important thing that you have to consider at the time of designing it. So take a pause, and then come back to the video. We will just discuss the architecture in detail. So if you are using like a Python library over here, the very basic architecture would look something like this. So the user, it will just ask what is the weather. It will go to that API gateway. It can be like a Flask or Fast API, Django, whatever the things you can use, like if you are using Python. And then it will go into the Redis or Dynamo. So what are the importance of the Redis or Dynamo here? Redis or Dynamo will hold all the conversation history, and not only the conversation history, all my WhatsApp chats. Okay, all my WhatsApp chats, some details around it might be in some threads. It will refer, so that suppose they say that suppose you have a friend called Sumit. So against the Sumit's name and ID, there will be some conversation, and you ask, when did I ask Sumit for a book? Okay, so this conversation should be able to do that. So all this internal details will be there in our DynamoDB, like only the response of the only the RAG response we will come later, but some sort of thread to connect with this WhatsApp chat will be there, and based on that it will keep on fetching the history. And once it fetches the history, after that this whole context, like your chat with the Sumit and your the other details, the other relevant details, everything will be passed on to the LLM. And then like for example here, so we are talking about the weather, so it will return that how good or bad the weather is, or what is the temperature in Fahrenheit, for example. Here it has returned. Now over there, as a backend engineer, what are the things further you have to consider? You have to consider the latency. So latency, why? Because if you just asking a simple question like what is the weather, that means it is very small. It can be like in 100 token. But the moment it comes with this sort of things like a conversation with Sumit, okay, then it can be like a 10,000 token or even 100,000 tokens. Okay, we do not really know. So maybe we will take like the last n chats, and we will give a disclaimer that this is the most we can process, because if we keep on processing that many number of things, the latency will definitely increase, and also the cost will go way more higher up. Okay, cost will just go high and high. So these are the two very basic problems that you need to take care. And also there are other things, like while you are doing a chatbot sort of a thing, the sliding windows sort of things also being implemented, like only the last 20 messages or last 100 messages. So the moment the 101th message comes, the first message on that list is totally go away. So these are the strategies that you could, if you are able to think through, then you are designing a great system. And of course I think you got the part, like why a increased number of context window will give you a linear increase in the cost. So we always have to take care of these things, like how big of a context window we are going to serve to users. So for the cost mitigations, what we can do is, like if you are using cursor these days, like there is a very strange thing you will see, like it keep on summarizing the chat. Anyway, we will try to build our own in the coming videos, and one of the coming lectures we will try to build our own mini cursor sort of a thing. It is not very difficult to build something like cursor. You will see it over the time, like how easy you can just get a system up and running like cursor. Okay, now coming into the cost mitigations and other things like this. Yeah, so other than cost mitigation, the context window, always we have to give a certain sort of a breaking point. For example, like when we are talking about the GPT-4 turbo, okay, it has a 128k, the highest context window. So like if your base LLM that you are using doesn't support that long of a context window, that means it will just fail, right? So you cannot really keep on just feeding data into your LLM while with an increased number of with an increased number of conversation in the conversation history, because the token will increase. So that is the breaking point you always have to think through. So now I think we have all the answers, like how would be the architecture, what would be the latency, how we can manage the cost, and what would be the breaking point. Like breaking point is always um, the context window size. So now, in our next section, we are going to deconstruct the GPT. So, what is the full form of GPT? I just wrote over here, that is Generative Pre-trained Transformer. And just understand, this is a very core technical term. It is not, I repeat, it is not a marketing jargon. Okay. So, the way we see, it is not a marketing jargon at all. Rather, it is a precise technical description of three fundamental architectural properties: this generative, pre-train, and transformer. Okay, so the moment we understand these three nuances, like all the other uh, uh, many of your mental fog will go away. Okay, you will start seeing the pattern, what exactly the LLMs are doing behind the scene. And okay. Without setting up so much context, let's do a deep dive. So, what exactly a generative is? Generative simply means this, that it creates the data. It doesn't retrieve anything from the database. So, if you remember, like while we were talking about this function, right? We talked that there is a function that we will have, and this function just keep on generating something, but it is not retrieving anything, right? So that is the very core part. The model creates the new data that didn't exist in its training set. And the contrast with the traditional system is, in the traditional system is generally a retrieval based. So it is a completely change from the traditional system, that from retrieval based it is now a generative based. Okay, so let's talk a little bit about this. So when we are talking about any databases, okay, like a SQL query or something, you will see that if you give a certain function, you will always get the same output, right? It will look up a index data and it will tell I can't find something, that's all. So this is, it is retrieving from a certain database, whereas this generative, this is completely based on statistics. And be GPT or the image, for the stable diffusion, or like generative music AI, all these things, what they are doing is they are doing some sort of a statistical pattern synthesis. So this term is again very important. It synthesizes the data. It is not retrieving any data. So I think you got the point how from a database system, uh, LLM differs. Like LLM keep on generating the data, so that is why we call it a generative. And why it is, what are the engineering implication of it? A generative model cannot tell you when it learned something. For example, in this sort of system, for the retrieval system, we have some sort of a source, that okay, this is the date updated of this particular record, and I can tell you that on this day I learned about this and take this data, like for this particular date this particular payment was being done against this particular order ID, and I know this got inserted in this XYZ date. But for a generative model, cannot really tell you that information, that when exactly it learned something. Okay, so this makes it unsuitable for the compliance heavy domain. Like the moment it goes for the legal and medical, you will see there are so many guardrails are being introduced. Again, what exactly is a guardrail, we will come in our following videos. Maybe like at the end there will be total 16-17 videos at least on this series. So the solution over there is, we generally go into the RAG, whereas RAG, we will cover in detail. It will retrieve the documents first, then the model generates using those documents which you can actually cite. So that is what the mean of the generative is. Okay, so now coming over here, what exactly a pre-trained is? Pre-trained is again one of the very fundamental property. That means the model is a frozen artifact, right? It was trained once on a snapshot of data or a snapshot of data set of a huge things like the Wikipedia article, so many books, everything that goes in there. And then there will be some weights that were saved onto the disk. And during the inference, like when you use it, the moment we pass something, that part is being called an inference. The weights do not change. Okay. So the key properties are it definitely have some sort of a knowledge cutoff. As you can see this part, the model only knows the data up to the training cutoff date. Like when GPT 3.5 took everything into Storm, it was, I think, had a training cutoff date till September 2021, but still it used to blow people's mind. Now with Perplexity, you can actually search the web also. So when you are passing something like that, it searches the web, it aggregates the data and gives you back. Then there comes like immutability, like you cannot teach it new facts by talking to it because the training is already being done and it is kind of a deterministic and given the same input. And if you mark the temperature as zero, temperature zero means like you are rejecting any kind of randomness. You can try this, it will produce the same output every single time. Okay. So in case like while using GPT-5, there is one of the very strange thing I saw like while developing something that was this sort of responses. So the model in 2021 Python 3.1 released in October 2022, right? Like that was the latest version. It was trained in 2021, but in 2024 also it was giving that the latest is that. But the truth was the latest was 3.12. So this sort of things, it is not exactly hallucination, but it is a fact-based inference, which it is giving. And one of the main problem with this is it has a catastrophic forgetting. If you continue training a model on new data, it often forgets the old knowledge. Like this is kind of a mathematical problem, like it comes with the forward feeding and the back propagation and everything. But just understand this thing, like even the researchers are working very closely on this. It often forget knowledge. Why and how, that is again little out of scope for the application engineers, but we cannot always depend. As an application engineer, our takeaway will be it doesn't always really depends on the particular um, uh, data it has been trained on. The moment some newer data comes, it might forget the older things. Okay. So so this uh, we have come to the most important part now, the transformer. So transformer is basically we are talking about the architecture. Okay. So this is the neural network architecture that was proposed or invented by Google in 2017 paper. Attention is all you need. So any AI engineer or any ML engineer, they must have uh, like heard about it or they discuss about it at some point of time in their career. So before transformer, what we had was we had RNNs, like the recurrent neural networks, and the LSTMs. So we will just take one example and understand, but just as a definition of transformer, just understand this thing, like it started processing all tokens simultaneously, right? So previously we saw that there is a sequential generation process. So here it started a simultaneous processing, and using this Google's paper in 2017, OpenAI came up with their the GPT, which took the market by storm. So it can scale up to billions of parameters, and the way it looks, when we will take a example and go deep into it, it will totally blow your mind. So let's take this example to understand it further. That so imagine you are reading a sentence. Okay. The sentence is something like this: the cat which ate the fish that was left on the counter finally fell asleep. So here few important thing you need to understand, like about the contextual thing. Co- like over here, which refers to the cat, that refers to the fish, and was left, when we say this part that was left, it modifies. So whom it exactly uh, modifies? It modifies the fish, right? And it doesn't really meant the cat. So all these things we have to understand in this. So this is kind of a long range dependency. The words far apart depends on each other, right? So was left is actually dependent on the fish. So there is that in between. Okay. So this is basically the processing of RNN and LSTM. So when we are talking about the RNN, like the recurrent neural network, and LSTM is a long short term memory. So what used to happen is they used to process word one by one. Like the process used to be something like the, from the cat, then which, then counter fell asleep in this way. So to connect which to cat, the model must carry the information across 3 plus step, right? So which is there, and then there is this cat, and also finally fell asleep. So who fell asleep? The cat. All this information has to carry till this point, right? So information degrades over distance. That is being called as a vanishing gradient, and that is again one of the mathematical problem of LLM. But the point is, this model, this sort of architecture had a lot of problem, like the RNN or the LSTM. So what happened with the transformer? The moment Google actually researched and proposed this, let every word talk to every other word and in an instant manner. So the core of the transformer architecture became this thing. Every word talk to every other word instantly. So what does it mean? Give me the entire sentence at once. I will load I will take every word, directly interact with every other words in a single step. And that is what we call as a attention. So this is, if I write it further, give me the entire sentence. I will let every word directly interact with every other word through a single step. And that is what they are calling as a attention, because every word is now attentive about each other. So now let's take a practical walkthrough. Suppose your input sentence is like this: the cat ate the fish. Okay. Now the goal is the predict the next word. Okay. So what does, if I mark something like a it was delicious, so what this it means? Okay. So suppose we mark something like it was delicious, what does it mean? So let's compare about how RNN versus the transformer would behave. Okay. So at the step 0, what happens? We know that the word is getting converted into token. So the cat ate the fish, it will get converted into something like this. Okay. It will get converted into this guy, right? Now, how RNN would handle this is, it will start with a hidden state. So for RNN, it will be h equal to 0, and it start taking everything sequentially. Like for example, the cat ate, and after taking there will total 6 token, because dot is also there. After taking 6 tokens, what it will do is, it will try to generate this it. Like this is a second sentence, right? It was delicious, so it is the first word. That with my GPT, this is the it is the word that I am trying to generate. Okay. So this is something that I am trying to generate. Okay. So this 6 token would take you to do the next word it. So here it's completely sequential. Even if you give, like you throw further GPU to it, it won't be able to utilize it because it's completely um, it is completely of no use because it is a completely sequential in nature. Okay, no use because it is sequential, right? So how a transformer would handle this? So now for transformer we have this, and all 6 token enter the model simultaneously, and each token get into a dense vector, and there is something called a positional encoding is also being added, as I told, that which is the first vector, which is the last vector, because fish ate the cat. Now why positional encoding is important? Let's discuss this part. If we mark something like a, if we do not add it, fish ate the cat and cat ate the fish, won't have any difference because they have the same words. Okay, so that is why with the dense vector the positional encoding is also important. And then the step 3, the most important part, the attention mechanism kick in. So for each token it asks which other token in this sentence should I pay attention to right now. Okay, so after this step, so this is one of the step happens. After this step, when the actual attention starts, it will tell you which other tokens in this sentence I should put my attention into. Okay, and like for example, what does 8 pay attention to? Like we will see that there will be high attention to cat, there will be high attention to fish, and definitely low attention to the dot, like this full stop that we had, right? So something like that we will have, that high attention in the cat, high attention to fish, but low attention to the dot. So this is computed via query and KV, that is the key value. Again, we are not going into a lot of details into that, but what happens behind the scene is, with all of these tokens are being computed parallelly with these 6 combinations, and one attention layer will be found which have a richer context than the other one. And gradually through this mechanism and through the feed forward network, it will found that okay, there is a full stop, then probably my next sentence, probably, like this will again give the probability, probably my next word would be a pronoun. Will it be a he or she sort of a thing? No, because we are here not referring to a person, we are referring to a cat, and we haven't specified anything like gender. All this information through the attention mechanism it will already get, and it will tell that might be it is a higher probability. Okay, so after that, like for example, it, they, this sort of things might come, and it will win as a probability. Through the softmax max function we will determine that the predict, it will predict that it part. So there might be, like in this whole process there might be some gray areas for you, but this is the very basic idea of that paper that was published, like the attention is all we need, right? So this is like, again, as a application engineer you do not have to understand all the details, but this should be your key takeaway, that now through the transformer architecture, why it is so fast, and why, like by throwing more GPU we will get better outputs, because RNN and LSTM it was sequential in manner, and there was no scope. Even if you are putting a lot of hardwares into it, there is no scope, because end of the day, if you just go into the core mathematics, it is just raw matrix multiplications that are happening there, nothing else, nothing more. So um, in one sentence, if I have to summarize it, the transformer replaces those sequential processing that used to happen for the RNN or the um, uh, other architecture like LSTM, and it creates a parallel. These are the important terms, like instant, parallel, and global communication between all the words. So why I use this term global? Because Like suppose you are giving like a 1000k context window, like 1000k words are there, like close to I don't know, like mm, uh, hundreds and thousands of different words are there. So how exactly the whole thing will come together? Okay, so that is why in the global, if we use this word, it gives us an idea that it uses this complete attention, this complete crisscross, and making it possible to train the massive context aware language, and that models that actually understand the long range meaning of it. And that is why attention is all you need, was not at all only a catchy title, and it was a revolution. And that is why whatever the place that we are standing right now in the in the LLM history, it is all because of that 2017 paper. So if you have further interest, go ahead. There are so many YouTube videos which have gone into a way more deeper into this, whatever the things that we have covered so far, that will give you a good further good or better intuitions. So inside the LLM black box, now we have a complete understanding of the pipeline. For example, in case we see some kind of a debug failure, then we might know that why a certain model is slow. So certain model is running slow because of there is some kind of a attention complexity it has run into, or like long context. Okay, this can be some probable reasons. So if we have to optimize the cost, so tokenization is definitely creating a lot of tokens. Like if we are going through a high cost, means like definitely more tokens are there. And then if I used to have some sort of uh, other architectural betterment, like to optimize high cost, what are the things we can do, all those decisions we can take now, if we understand what is happening inside the LLM black box right now, like all the mechanisms, that how from one layer to other layer the data is going into LLM, and what exactly LLM is doing behind the scene, and how exactly it keep on increasing the context and returning you the data. So far so good. This is the thing that I wanted to discuss, and it is already almost like a 1 hour 20 minutes video. But if you have made till this, I'm sure like you have learned a lot of foundational ground on generative AI. So see you in my next video. Till then, stay awesome. Bye.